I want to start the history, so I have some thesis to present. Of course, I'm neither a historian nor am I really a philosopher, even though I studied philosophy at some point. But I want to start my story with a thesis that people have always been able to argue in a reasonable, coherent, and rational way about mathematical objects. We will see, or you all are aware of the fact that mathematical objects are very abstract. So let me try to write. So I suppose that you can read this, and this is all I will be doing. I will write on this tablet and produce my notes here, and later I will make the notes available. Okay, mathematical objects are very abstract, but still we can reason about them in a coherent and rational way. And in fact, as we will see, or as we are all aware, the mathematical objects are not the only objects in this world which are very abstract. So if you want to take that as an argument against the reality of mathematical objects, then a lot of things in this world would kind of fall. I mean, if you think of other sciences or even everyday life, you know, if you start thinking about to which extent is, let's say, money, which we use every day, a concrete object. It's not very concrete, it's a very abstract entity. The money we pay with, the money we deal with, if you pay with WeChat, what does it mean for that money to really exist? It's a very abstract concept. Or if you take the concept of a country, if you take the concept of the People's Republic of China, it's a very abstract entity, right? I mean, you cannot really see it. I mean, but still you have some way to, you know, it's a very real thing, right? So you can talk about it and it exists. Anyway, mathematical objects certainly are abstract. They are the prototype of abstract entities, but still people have always been able to talk about them in a reasonable way. So mathematics really started with the Greeks, and they mostly were interested in geometry. It seems that they were kind of, I don't want to say afraid, but they hesitated introducing the real numbers, even though they were kind of, it was just there. It would have been just one more step. So the Greeks mostly did geometry, but there is also arithmetic or number theory in the famous book by Euclid. So Euclid is this person who, I'm not sure if I should answer the question which show up in the chat. This will be, you know, I will start with number theory and we will get to set theory very soon, okay? It's not a talk about number theory, but I will start out with number theory. There is some number theory in Euclid. Euclid is this guy who wrote the books about geometry, namely, for instance, there is the proof that there are infinitely many numbers. I'm sorry, that there are infinitely many prime numbers. And there is a reason why I want to show you this proof. We will get to that later. So suppose, so now I should be able to move this up. Yes, okay. So suppose you have, you give me finitely many prime numbers, P1 up to Pn. I can look at the product of them, right? So let Pi up to Pn be prime. Then just look at the product of them and add the number 1, right? So the observation which was made, and this goes back to times before Euclid, certainly he was reporting this argument, then none of the pi for I between 1 and n divides this number, which let's call it q, okay? Q is the product of the pi's plus 1. But then you also have the fact that every number bigger than or equal to 2 can be written actually in a unique way as the product of primes. So also this q can be written as the product of primes, but none of the primes p1 to pn divides it, so there must be another prime. So as q can be written as a product of primes, there must be a prime different from all of the pi's. Okay, so if we look at this argument, this proof kind of presupposes that you're able to talk about natural numbers and about primes, right? You presuppose that the natural numbers, they are just out there. They are there as some kind of totality, as some entity, and we can reason about them, right? This is a very easy proof, which you can tell to not even an undergraduate, which you can tell to a student in school, maybe even in primary school. So, and it also tells us that, without much theory, you just need to know a little bit about numbers and primes and products. It's very easy to follow this proof, right? And this attitude towards number theory hasn't changed over time. So we have a very clear intuition about the natural numbers. So let me write that down. I hope you can read my handwriting. We have a very clear intuition about natural numbers. And of course, once you have the natural numbers, you have the integers, the positive and negative integers, and then you can make sense of the rational numbers, which are very easy to grasp. And then we get very quickly to the point where the Greeks hesitated to go further, right? So the Greeks observed in some kind of geometric way that the square root of 2, for instance, is not a rational number. But they, as I said, they, for some reason or the other, they hesitated introducing real numbers in the abstract, right? So this was done much later, starting to talk. I mean, first, then, throughout history, then people kind of started working with these objects with the square root of 2 with more complicated real numbers, but they never really developed the kind of pure theory of these real numbers. And this was done much later in the 19th century through work of, for instance, Richard Dedekind, or also Georg Cantor, who is the founder of set theory. So the real numbers we write R for the set of real numbers were introduced much later through Dedekind, Cantor, and so on. When I say introduced here, I really mean that the pure theory of them was developed. People were computing, calculating with them much earlier, of course, right? But they never developed the pure theory, okay? Now I want to I want to point out that when you move from the natural numbers or from the rational numbers to the real numbers, it's really a step in abstraction. And it's also a big, I mean, it is a step if you think set theoretically, if you define the real numbers from the natural numbers and the rational numbers, you need set theoretic operations which take you beyond the natural numbers. I will come to that in a second. But first, let me state that you know, this step of abstraction, what it really needs is the following. I mean, the proof we saw before about the of the fact that there are infinitely many prime numbers. This is a proof about numbers. So your reality are the natural numbers when you do this proof. You don't need the set of natural numbers to exist, or the natural numbers as a totality, as a mathematical object which you can reason about. You only reason about numbers. But when you want to introduce the real numbers, you go outside, and this is a typical step which shows up when mathematics has some progress, or when mathematics develop. You have a realm of objects, in this case the natural numbers, and then you're kind of inside, you see the natural numbers, but then you step outside and you look at them and you make them an object of research. So you first you talk only about natural numbers, and then you talk about the natural numbers as a totality, and you start talking about sets of natural numbers. So this is a step of abstraction which is very natural in mathematics and in other fields of science, and also in everyday life, right? So you work with a group of objects, and then you step outside and you see them from outside, and you make them the range of quantifiers, if you want. Okay, so if you let's study this a little bit, and this will bring us to the proof of Cantor that there are more real numbers than rational numbers, right? So Cantor introduced the real numbers through what he called, I don't know how you would translate it into English, Fundamentalfolgen. Nowadays, these things would be called Cauchy sequences. So let's take a quick look at what happens here. So if you don't yet have the real numbers, but you want to introduce them, what do? So a Cauchy sequence is a sequence of rational numbers. So Q denotes the rational numbers, such that, and you all know the definition, you want to say that the sequence converges, but you don't have the objects yet where it converges to. So what you say is that for every positive epsilon, there is a natural number n0, so that for all n and m which are at least n0, the distance between qm and qn is less than epsilon, right? This is a Cauchy sequence. And then what you do is you define an equivalence relation on the set of all Cauchy sequences. So you say that, if we abbreviate such a sequence by, let's say, Q vector, then you would say that Q vector is equivalent to Q vector prime, if and only if, while they come closer and closer to each other. So you would say that for every epsilon, there is an n0, so that the distance of Q prime n to Qn is less than epsilon for all n at least n0, right? You all know this definition. Okay, so if we look at this kind of theoretically, abstractly, what is going on? You start with the natural numbers. It's very easy to form the rational numbers as pairs. You want to put a sign in the front, okay? But then if you go to the real numbers, and there isn't really any way different to that, what you do here, if you do it like Cantor, you first talk about sequences of rational numbers. So this is one step up, right? You cannot anymore talk just about natural numbers. You have to talk about sets of natural numbers or sequences of natural numbers. And then you do another step. You look at equivalence classes, right? You can do it a little bit differently, but what's going on here, if you do it that way, is basically in the set theoretic hierarchy, you move up actually 2 steps if you do it like Cantor, right? You talk about sets of natural numbers or of rational numbers, and then you talk about equivalence classes, which are sets of natural numbers or rational numbers. Okay, and the real numbers may then be identified with the equivalence classes given by this equivalence relation. So they may be construed as equivalence classes of such Cauchy sequences. So these are just all the sequences which are equivalent to a given sequence. All these Q vectors here are Cauchy sequences. And then you can prove then we may prove things like the nested interval principle, which will be important for us. So the nested interval principle says that if you have a sequence of closed intervals, so let me write them like this. Is a sequence of closed intervals with real endpoints. Okay, an and bn are real numbers. An is strictly smaller than bn, and we want to have that, you know, an. So the next interval always sits within the earlier interval. So it looks like, whoops, there should be a less than or equal. It looks like this, right? an, bn, an plus 1, bn plus 1. Then the conclusion is that the intersection of these intervals is non-empty, and this becomes a provable fact. Often when you do calculus in the beginning, you state this as an axiom or something, but when you introduce the numbers as we did set theoretically, then you can actually prove this kind of thing, right? So what we did was, if we step back and we summarize again, right? We start with the natural numbers, we go to the rational numbers, which is just a very tiny step away from the natural numbers, and then we do 2 levels of abstraction, or 2 layers up the power set operation. So this is an up, the power set operation, right? You talk about sequences of rational numbers and then equivalence classes of them. This brings you to the real numbers, and then you can prove these principles. And then once you have this principle, Cantor came and actually proved that with the help of this principle, you can prove that there are more real numbers than rational numbers. Or for that matter, than natural numbers. You might say this is an argument, or this is a theorem the Greeks could have arrived at if they had been courageous enough to introduce the real numbers, which they didn't, because the proof, I would say, is not that much different or harder to the proof we just saw of the proof that there is an infinity of prime numbers. Okay, so let me show you how to do the first proof which Cantor gave for this fact. Probably most of you know it, but you know. So the proof he gave is that you do exactly what we discussed before, that you consider a nested sequence of closed intervals. So suppose you have your favorite, you know, take a function from the natural numbers to the real numbers. In size, there is a bijection between the rational numbers and the natural numbers. So let's work with the natural numbers here. Okay, suppose you have this. So let's just write xn for the value of this function at n. And then you simply produce a sequence of nested closed intervals as above. You know, they sit inside each other, but you just want to make sure that the nth point is outside of the nth interval. And that's completely trivial to arrange, right? If you know, you have x0, which sits somewhere, you just start with an interval which is, let's say, here, right? And then if x1 sits inside this interval, well, you just shrink the interval in such a way that x1 is outside. And you just continue in this fashion, right? And then in the end, if you take an element of the intersection of these intervals, which we saw exists because it's non-empty, well, this xn is in all the intervals from an to bn, and therefore it's different to xn for every n, right? So x is different to xn for all n. And this is actually historically the first proof Cantor gave, right? So it shows that the function f we started this with from the natural numbers to the real numbers cannot be a surjection. And therefore there are more real numbers than natural numbers. So this proof is as clear as and convincing as the proof that there are infinitely many prime numbers. And it's not clear to me why once in a while there are people challenging this proof. So the point here is that Cantor proceeded, and Cantor and other people at the time proceeded with this natural step from, you go from inside to outside, in the sense you have a realm of objects which you talk about, but then you step outside and you make that realm of objects, that set, you make you know, the object of your generalized discourse. So you move on from the natural numbers to the real numbers, and then Cantor actually, you know, went all the way. And this is his achievement, that he said, this has nothing to do with natural numbers. This has nothing to do with real numbers. We can always, you know, we can always go, we have a set, we move on to the power set, right? You have the set of natural numbers, you move on to the power set of the natural numbers, which corresponds to sequences of Cauchy sequences. And then you move on to the power set of the power set. And this corresponds to the real numbers. And you move on and you move on. Okay. So Cantor also, so Cantor, this was Cantor's insight, and Cantor also introduced the concept of cardinality, right? So he removed the paradox that a given set, that you can have a set which is a proper subset of another set, but A and B have the same size. What do I mean by he removed the paradox? You know, I mean, if you talk about it naively, there was always given the example of the primes. If we go back to the primes, right? We show that there are infinitely many prime numbers. Okay, fine. So that means that there is a bijection between the natural numbers and the prime numbers. But wait, on the other hand, the prime numbers is a proper subset. Not every natural number is a prime number, right? So it's a proper subset. And people thought this is kind of paradoxical. Well, it's only paradoxical if you're used to the finite, right? It doesn't happen for finite sets. If you have a finite set, there is no proper subset which has the same size. If you have a set of 17 elements, a proper subset may have 5 elements, and there is no bijection between them. But for infinite sets, no problem. Okay, and Cantor taught us that for infinite sets, the world looks very much different. And he showed us that you can very easily develop the first steps of a theory of cardinality. Two sets are said to have the same cardinality if there is a bijection between them, and that's a equivalence relation, and you can start working with investigating this equivalence relation, and this leads to the theory of cardinals and cardinalities, and this brings you to the questions of cardinal arithmetic and so on. Okay, but it also led to Cantor's most famous problem, which was mentioned very nicely in the introduction to the continuum hypothesis, to the continuum problem. So this says continuum problem. Numbers, the natural numbers. Okay, so the question is, what about, can you have a set A, a set of real numbers, such that A is uncountable, but A and the reals don't have the same size, so there is no bijection. Right? So having the same size means that there is a bijection between them. So can you have a set so that there is no bijection with the natural numbers, yet there is also no bijection with the real numbers, so it kind of sits in between. It turned out, Cantor asked this question, and it turned out that this is a very difficult question. Cantor was trying to attack the question unsuccessfully for many years. So but on the other hand, he did make some progress. Cantor did make progress on this question. There is, for instance, the theorem which is nowadays attributed to Cantor and Bendixson. That if you have a closed set, if A is closed in the order topology of the real number, so a closed set is the complement of an open set. An open set is the union of open intervals, of a set of open intervals. So if you take a closed set can be fairly complicated in some way. If A is closed, then either A is at most countable, or A and R have the same size. And then later, this is basically where Cantor got stuck. So that you might develop the idea, well, why don't we prove the continuum? Why don't we answer the continuum question, you know, whether there could be a set A which sits between the reals and the natural numbers? Why don't we look at more and more complicated sets? And this was actually a very good program. You know, instead of doing this full generality, the step in full generality in one step, do it in small steps. You know, instead of looking at arbitrary subsets of reals, sets of reals. Look at very concrete sets of reals to begin with, and maybe something will emerge. Maybe you will get a better understanding of sets of reals. And this was a very nice program. So it turned out that this theorem, this may be generalized to more complicated sets, to Borel sets. In fact, by Suslin, to what's called analytic sets. Analytic sets are already very complicated. They are beyond the Borel sets. So an analytic set is you are in the space R to the R. You take a Borel set here, and you project it on one coordinate. I don't want to give the formal definition because it doesn't play a role for us. I just want to indicate that these can be fairly complicated sets of reals. So you project a Borel set in R to the 2 onto, let's say, the x-axis, and this is an analytic set. And for them, also the continuum hypothesis is true. The continuum hypothesis saying that there is no set which is in size between the natural numbers and the real numbers. Okay, so the question, but this is where the story ended in the early 20th century. So people were not able to generalize this result further. So there was Cantor-Bendixson, there was a lot of work to arrive at this result for Borel sets, and then in the end for analytic sets, and this is where people got stuck. Okay, and there was a reason why they got stuck. We now know why they got stuck. But anyway, the question of the continuum problem . The continuum problem. Well, I'm not sure. Let me be a bit courageous here and say that it's the driving force of set theoretical research. You can argue about that, and I don't care. It is certainly one of the key driving forces. A lot of questions kind of go back to the continuum problem, are kind of simplified versions of the continuum problem, or arose out of questions which have to do with the continuum problem. Of course, there are other questions, no doubt about that. But somehow behind a lot of things we do in set theory is the continuum problem. Can you have a set of reals which is in cardinality between the natural numbers and the real numbers? Okay. So to summarize, at this point of the talk, the objects of mathematics are very abstract, but Cantor showed us how to talk about objects with mathematicians talk about all the time, namely natural numbers and real numbers. They can be made precise. You can reason about them very precisely. And even though the objects of mathematics are abstract, we saw in the beginning, well, there are other objects in everyday life, even which are very abstract. Or if you take physics, right? I mean, what the physicians, like the physicists talk about, like particles or quarks or black holes, singularities, the beginning of space-time. This is all very, partly it's pretty speculative. And if you compare with what we in mathematics talk about, it's not less abstract. And it's not kind of that physicists talk about, the objects in which you can touch or whatever. It's very abstract. Okay, so now let's move on and talk about modern aspects of the continuum problem. Okay, so Gödel, or let's say more modern aspects of the continuum problem. So Gödel showed in the 30s that CH, this is the continuum hypothesis, and the continuum hypothesis is the statement that if A is a set of reals which is uncountable, then A and R have the same size. There is a bijection between them. That CH is not refutable, is consistent. Well, consistent with what? By that time, people had introduced an axiom system or several axiom systems. There was one prominent axiom system of set theory. Cantor didn't work with an axiom system. He worked not axiomatically. He argued about sets as, as people often and still argue about natural numbers. You have such a concrete intuition about natural numbers that often you say, well, I don't really need an axiom system. And also Cantor had held this kind of position that, everything is so intuitive that you can just start reasoning, and it's very reasonable to do it that way for a while. But anyway, people had introduced an axiom system, and the axiom system, which we use nowadays mostly, is called ZFZ. This is our standard axiom system of ZFZ, of set theory. Okay, but simultaneously, Gödel actually didn't believe that CH is true. Gödel, at least for parts of his life, that's for sure, believed that CH is false. In fact, and now I'm start using set theoretical notation, the cardinality of the real numbers is denoted by 2 to the Aleph 0. This is the cardinality of the real numbers, that this is, so the infinite cardinal numbers, they come in a well-ordered hierarchy. You can prove in the presence of the axiom of choice. The smallest infinite cardinal number is the cardinality of the natural numbers. It's denoted by Aleph 0. It shows up in the exponent here, 2 to the Aleph 0. So this is the cardinality of the set of sequences of natural numbers or of subsets of natural numbers. The next infinite cardinal is Aleph 1. So if the continuum hypothesis holds true, then this is equivalent to saying that 2 to the Aleph 0 is equal to Aleph 1. But if you say that 2 to the Aleph 0 is bigger than Aleph 1, this means that between the size of the reals and the size of the natural numbers, there is a cardinality in between, and this negates the continuum hypothesis. So Cantor actually thought that the continuum hypothesis is false and that 2 to the Aleph 0 is actually Aleph 2, and therefore, because he thought it's true, he also thought that the continuum hypothesis is actually independent of the axiom system ZFZ, right? And this was confirmed later, the view that CH is independent from the standard axiom system ZFZ was confirmed by Paul Cohen in the 60s, who developed the theory of forcing, which got used to show that, for instance, 2 to the Aleph 0 is equal to Aleph 2 is consistent with the axiom system ZFZ. And okay, this is the situation. This was the situation. Then you had a axiomatization of set theory ZFZ, which did not decide the continuum hypothesis. Does it mean that we cannot reason about sets anymore? Does it mean that sets are only given through an axiom system? I would say it's exactly the other way around, right? I mean, we have a very clear intuition about sets and about the generation of sets, right? from the natural numbers or even from the empty set by the iterations of the power set axiom. And we can reason very well about these things. So we have some kind of intuition, we have some access, like we have access to other abstract things we deal with. So what is the what is the way to go here? How do you deal with the situation of independence? Well, Gödel's credo was that, okay, the conclusion is that ZFZ is just not strong enough to decide it. We need a more powerful system. We need more intuition. We have to sharpen our intuition. We have to introduce new axioms. There is a quotation which I want to write down in full because it's very interesting. So this is a quotation of Kurt Gödel. So he said that one may, on good reason, suspect that the role of the continuum problem in set theory is or will be this: that it will finally lead to the discovery of new axioms which will make it possible to disprove Cantor's conjecture. Okay, this is a sentence which you can read more than once. So it talks about the fact that, you know, the role of the continuum problem, it kind of forces us to strengthen the axiom system ZFC, that you look for natural. Of course, you can just write on axioms by inventing them and say, this is my axiom, but you want to have a natural axiom. You want to have an axiom which kind of coincides with your intuition about sets, which you know, is a natural thing which produces the right theory, and there are ways to discuss these questions. So this is about new axioms, and which will make it possible. He doesn't say to decide, he actually says to disprove Cantor's conjecture, right? The approach you might take then is a little bit like in physics or in other areas of science, right? I mean, you don't know like in other areas of science, you don't get there, you write on an axiom system, you know, somebody tells you the full truth, and then you have the full truth on your side, and you only have to prove things from the axiom system. This is not how it works. And actually, by Gödel's incompleteness theorems, this is not how it can ever be. The thing is that you start trying out theories, like in physics. You develop theories, they look natural, they coincide with what you would expect for other reasons. They give a certain picture, and you just try it out. You do it a little bit playful, right? And this is exactly what happened since Cohen discovered or developed forcing. So in the remaining time of my talk today, I want to discuss an approach which actually might be construed as fulfilling Gödel's program on deciding or disproving Cantor's conjecture. So over the last decades, such axioms emerged. And let me write down what they are. And I was told that we should make a break at some point. I will say a little bit more here, and then maybe we can make a 5-minute break and then continue after the talk with discussing what I'm now outlining here. So I want to talk about forcing axioms. And they go back to work of many people, but essentially the forcing axiom I want to talk about is due to Foreman Magidor, and Shelah. You know, when I write this down, I'm not writing down the whole history. It's just the culminating work on what's called Martin's maximum. This is due to these three authors. And there is another set of axiom, or in fact one axiom. It has the unfortunate abbreviation star. It is an axiom which is due to Hugh Woodin. Okay, and this is what we would like to discuss after the break. So I would suggest, even though it's a little bit earlier now, we make a like 5-minute break and we reconvene in 5 minutes. Is that okay?
Yeah, it's okay. 5 minutes break. Okay.
Okay, great. Okay.
Okay.
Of set theory or of mathematics, even though they are very abstract, we all agree on that. They do exist. We can reasonably and coherently argue about them. And because of that, you can be never satisfied with the fact that you have a given axiom system and that's it. You want to kind of answer questions. These objects exist independently of the axiom system. The axiom system is there in order to answer questions about them, but you don't expect that a given axiom system answers all the interesting questions. It's formally, it's also never complete, right? Okay, so we arrived at the question of the continuum problem, continuum hypothesis. We saw that Gödel didn't believe that the continuum hypothesis is true. I wrote down this famous quotation by Kurt Gödel, where he says that we should look for new axioms. Of course, what he wants here is not just an axiom which decides something. He wants a natural axiom. You can have a discussion about what does it mean for an axiom to be natural. So this is, there is room for a lot of discussion here, of course. But what I want to show you now is 2 examples of arguably natural axioms which have been around for quite a while. And you know, what often happens is that in every field of science, if you have allegedly competing theories and then eventually you show how to merge them, how to unify them, this supports the theory, right? It always supports the theory that, you know, you have kind of allegedly competing theories, and then all of a sudden you see, well, it's kind of, it can be merged. It's kind of the same theory, and it explains a lot of things. So this is exactly what happened here. So the forcing axiom part and the star part, they were kind of, they were approaches to, you know, to spell out the same kind of philosophy. And a result which I want to present towards the end of this lecture is that these are actually, you can unify. And this, in my view, this supports the view that something true is going on here. Okay, so let's discuss these things. So both the forcing axioms, both set of axioms, spell out the principle maximize. You know, if you look for a new axiom, you need some kind of principle. I mean, you know, you need to some kind of guideline. So one of the principles comes from, may actually go back to Gödel. So what Gödel did in order to show the consistency of the continuum hypothesis is he produced his constructible universe, which is usually called L. And this is the counterexample of maximizing. He kind of minimized. He produced the least model, which can be a model of set theory. You only put the sets in which are really necessary in order to arrive at a model of set theory, at a model of CFC. This is what he did. So this is kind of against our intuition that, you know, you want to take all the sets of natural numbers. You want to take all the sets of reals. So there should be more than just the ones which you are forced to put into a model. More than the ones which are definable and then definable in a more complicated way, more than the ones which are definable from ordinals and so on. Okay, so this is, they spell out the same principle, maximize. So in the case of the forcing axioms, it looks a little bit different to the case of the star axiom. And of course, as time is short, I cannot tell you everything about them, but I want to try to give you an idea. Okay, so let's turn to the forcing axioms first. Okay, so we have the forcing axioms. So the standard forcing axiom, you may construe, and I don't want to say something about that, you may construe that as a generalization of the bare category theorem. The bare category theorem saying that if you have open dense subsets of real numbers, then their intersection is dense, and the proof is just a variant of the proof of Cantor that there are more real numbers than natural numbers. So it's basically the same proof, and generalizations of this principle to higher cardinalities yield the forcing axioms. So the first forcing axiom was Martin's axiom. And for some reason or other, I want to put an index here, namely omega 1. So this is the axiom which says the following. So now I kind of presuppose that you have a little bit of knowledge of forcing. So before the break, I didn't presuppose anything. Now I presuppose that you know a little bit about set theory. I cannot introduce these things by lack of time. So let me presuppose that you know forcing. So Martin's axiom talks about forcings which satisfies the countable chain condition. And it says that if you have a forcing which satisfies the countable chain condition and you have L of 1 many dense sets, then there is a filter which meets them all. This is a generalization, as I said, of this bare category theorem. For instance, Martin's axiom sub omega, where you would only have to meet omega many dense sets, would be a provable theorem of CFC. So this is some kind of maximizing the principle that you want to meet a lot of dense sets, at least in a CCC forcing. Okay, and then people relaxed the requirement that the forcing be CCC to arrive at more powerful forcing axioms. So you have the proper forcing axiom, and there is no index omega 1 here anymore, and I will tell you why in a second. So this is the proper forcing axiom. Okay, in the case of Martin's axiom, you can also say, I want to meet more dense sets. You give me a collection of L of too many dense sets in a given forcing which satisfies the CCC, and then I have to give you back a filter which meets them all. This is still a consistent statement. The proper forcing axiom says that the same would be true for proper forcing. So the proper forcing axiom formally says that if you have a proper forcing, and a proper forcing is a generalization, you relax the concept of being CCC. If you have a proper forcing and you have L of 1 many dense sets in the proper forcing, then there is a filter which meets them all. Now you could try to replace the L of 1 by L of 2 here, but then you get an inconsistent statement. And this is the reason why there is no index anymore. And this is something I want to talk about in a second. So you have a strengthening of the proper forcing axiom, which is called Martin's maximum. You know, the name certainly comes from Martin's axiom. So this was Martin's maximum. This is arguably the most powerful forcing axiom in some sense. You cannot enlarge the class of forcings anymore unless you want to get an inconsistent statement. So Martin's maximum is exactly what these guys introduced. Okay, you can strengthen it a little bit further. A technical strengthening of Martin's maximum is Martin's maximum plus plus. And I don't think I want to formally define it, or maybe I should. So let me state Martin's maximum double plus, because it will play a role in what comes. So the statement is the following: let P be a forcing which preserves, and now I need the concept of a stationary subset of omega 1, which preserves stationary subsets of omega 1. A stationary subset of omega 1 is a subset which meets every club subset of omega 1. So we need the theory of a little bit of the theory of stationary sets. And let D be a collection of size LF1 of dense sets. So they are dense in the partial order in the forcing P. There is then a filter G such that G meets all the DIs for all I in omega 1. And I told you this would be Martin's maximum without the plus plus. There is a moreover part. If you have names tau I for sets of reals, for stationary subsets of omega 1 is a collection or a sequence of names in the forcing of P names for stationary subsets of omega 1, then the G interpretation, which is just the set of all xi, so that there is a, well, then I should say G may be chosen in such a way that the interpretation of the name, which is just all the xi, so that there is a P in the filter, so that P forces that xi is an element of tau I, that this is a truly stationary set. Now there is an equivalent formulation of that, which I want to write down, which is trying to show you that, this is something which is along the lines of the principle maximize. Here is also kind of transparent, right? You want to meet many, many dense sets. Okay, fine. So equivalently, if the forcing preserves stationary subsets of omega 1, and suppose you have a model and that phi be a sigma 1 formula. So a sigma 1 formula is a formula which says that there is something, there is an object, blah, blah, blah. So suppose P, the forcing, forces that the sigma 1 statement is true about the model M, then, well, you would like to say the conclusion is then phi of M is already true, but this cannot be. For instance, you might look at the statement that the omega 2 of the universe gets collapsed to omega 1. This is a sigma 1 statement in the right parameters. So you can throw everything into a model. And then this statement cannot be true in B. But what you can say is then there is a model M bar of size at most Aleph 1 and some elementary embedding J from the model M bar into M, such that the sigma 1 statement holds true about M bar. So now I have to, I would have to make it a little bit more precise. So the model M to begin with has to have arity Aleph 1. So there are at most Aleph 1 many relation symbols or function symbols or constants. And then the same would be true for M bar. It has the same signature. Also, what I want to say that if, what does it mean for phi to be sigma 1? This would be actually sigma 1 in the language of set theory, but you may also add, and this is where the plus plus comes in, a predicate for the non-stationary ideal on omega 1. So you have symbols for that. So this saying that something is stationary or non-stationary doesn't cost you a quantifier in the sense of this sigma 1 hood. Okay, and then this is an equivalent formulation, and it kind of shows you that it's a maximality principle. Okay, you can start playing with it. It turns out that this axiom decides a lot of questions. So for instance, I had this list up there that M is the strongest of them. The weakest one was Martin's axiom omega 1. This already implies that the continuum is at least Aleph 2. So it confirms parts of what Gödel was conjecturing, namely that the continuum is Aleph 2. And this fact is actually very easy to prove once you have Martin's axiom. For this, you can use the forcing, which was originally introduced by Paul Cohen to show the independence of the continuum hypothesis. You show that you use the Cohen forcing, and assuming that there are Aleph 1 many reals, the Martin's axiom will tell you that, well, there must be another real. So you may look at Cohen forcing and you write down the dense sets which run away from all the given Aleph 1 many reals. So you deal with Aleph 1 many dense sets and you get another real. So there cannot be only Aleph 1 many reals. There must be at least Aleph 2. It turns out that the stronger forcing axioms actually decide the size of the continuum. And this is also why there is no index anymore. It decides, for instance, Martin's maximum, and in fact, even the proper forcing axiom, but I want to write it down that way. Martin's maximum implies that the continuum is Aleph 2. And I actually was planning to give this as my only proof. It's not an easy proof, but it's a very nice proof. So how do you, but let me, instead of giving you the full proof, let me outline how you do such a thing, okay? And maybe then you get curious and you can go to the actual proof. So how do you prove such a thing? So the easiest way to prove that, and I said this is not the strongest result possible, but I think this is the easiest way how to prove that one of the forcing axioms decides actually the value of the continuum. So you need a little bit of structure. You want to count the set of real numbers. Actually, what you want to count is the set of subsets of Aleph 1. So you start with a collection, a splitting Ti, I less than omega 1 of omega 1 into stationary sets. This is a result due to Solovay that you can always do that. You can actually split every stationary set into omega 1 many stationary set. I'm talking about stationary subsets of omega 1 here. And then you start also take a set S, which is a set of, now I'm using the notation so S to the omega sub omega 2, these are the ordinals below omega 2, which have cofinality omega. So you take a set which is stationary and co-stationary. Okay, and now what you want to do is you want to show for every subset of omega 1, let's say, which is non-empty, and maybe I think it could be everything, but let's say it's not everything. I think it could be everything, it's fine. You want to show, using Martin's maximum, that there is a continuous function f from omega 1 into omega 2 is a continuous function which is strictly increasing strictly increasing means that the values become bigger and bigger. Continuous means that at limit stages, you are the supremum of the values before. So there is this kind of function such that what you want to have is that xi is in the union of the ti's where I is in your given set X if and only if f of xi is an element of your given set S. And actually, I want to have that the function, not only it goes there, it actually goes into this thing, okay? So in other words, you are in the union of the ti's where the index I comes from X if and only if f of xi is in S, and otherwise you're outside of S. You are in the relative complement of S. Okay, and then you can say, so I invite you to go through these arguments. Once you have that, it's a nice argument. We let alpha x be the supremum of the pointwise images of this function. For any, for every capital X, you have such a function f, you choose one, you let alpha sub x be the supremum, and then you simply show that the function which takes capital X to alpha sub x is injective. It has to be injective. What does that mean if it's injective? You have 2 to the aleph 1 many such sets, capital X, because you are going over the subsets of omega 1. And the ordinals alpha, it's the supremum of this function. This supremum is always less than omega 2, right? It's an ordinal of cofinality omega 1, which is below omega 2. So it's an element of omega 2. And you have omega 2 many such values. So if this is an injection, you have an injection from the power set of omega 1 into omega 2, and therefore 2 to the aleph 1 is actually equal to aleph 2. But you also, we already saw that Martin's axiom sub omega 1 already implies that the continuum is at least aleph 2. And if 2 to the aleph 1 is equal to aleph 2, 2 to the aleph 0 cannot be bigger. So we have the following, right? Actually, this part of the equation is called Ellucian's hypothesis. Which is another thing I did not mention before. I should have done it. Ellucian conjecture that this is true. This is a weakening of the negation. Well, it is a form. It is a strengthening of the negation of CH, but it's a weakening of the statement that 2 to the aleph 0 is actually equal to aleph 2. So it sits in between, right? So this is what this forcing axiom decides. Where do you get this function little f from? Well, you get it by forcing. So you write down a forcing which produces such a function by countable approximations. So this is your forcing. Then you write on the right dense sets, and you show that if you have a filter which meets all these dense sets in question, then this produces you a function as desired. So this is not very hard to do. Okay. So in the remaining 10 minutes, I was trying to talk about the other axiom a little bit. Let me just say that there are other consequences of Martin's maximum, or Martin's maximum double plus for that matter, which I might write down. So Martin's maximum implies a lot of things. The point is now, if you don't know what these things are, it doesn't matter. I just want to point out that there are a lot of statements structural statements which are implied by Martin's maximum. There is something called the admissible club guessing principle. There is a principle saying that U2 is omega 2. There is something, I'm sorry, the arrow should go from here. Let me erase. Okay, omega 2. Whoops. So sharps for reals. There is the club bounding principle. There is a statement called phi AC. There is a statement called psi AC. Psi AC is a localization of the principle we essentially just showed to follow from MM to decide the size of the continuum. So these two things are principles which also both decide that the continuum is LF2. And there are other natural statements. Let me just mention, there is a statement, for instance, that for every subset of omega 1, there is a B, another subset of omega 1, which is amenably closed. Amenably closed means that for all C subsets of omega 1, if for all psi less than omega 1, C intersect psi is an L of B, then C is actually an L of B. This is what it means for B to be immediately closed. If that's true, then for all A, there is a B which is amenably closed such that, such that A is an element of L of B. So it was not known if A follows from Martin's maximum or Martin's maximum double plus for that matter. There is another principle that every stationary co-stationary set modulo a real is equal to a generic collapse of the omega 1 of V over L of that real. And there are other consequences, very nice consequences of Martin's maximum or even weaker forcing axioms. For instance, there are no Suslin lines. The union of less than continuum many null sets or meager sets is null or meager. There is a non-free Whitehead group. Justin Moore has shown that there is a 5-element basis of the uncountable linear orders. Farah has shown that every automorphism of the Cauchy algebra of a separable Hilbert space is inner. So there are a lot of structural consequences. So it's a very, it's a principle which decides a lot of very natural questions, also from other areas of mathematics. It's not limited to the, it's not limited to set theory, and it's not limited to set theoretical topology. There are other areas of mathematics where you get answers. But there were principles like this principle A here, which were not known to follow. So there was a competing axiom. And unfortunately, I will not have the time to discuss this axiom. So it's very difficult to swallow what the axiom actually says unless you start working with it and you see the context where it arose out of, and you see how it works, how to apply, how the axiom functions. And it's also more difficult for the following reason. The principle we just saw, namely Martin's maximum, I didn't say that it's a consistent principle. I hope you were expecting that it would be consistent, right? So how do you show the consistency? In this case, what you can do is you start with a large cardinal, in this case a super compact cardinal, and you do a forcing over a model with a super compact cardinal, a model of ZFC with choice, and you force Martin's maximum, for instance. This did not work so far with the principle we are about to write down now, namely the star principle by Hugh Woodin. There was no known way how to force it over a model of CFC. Nowadays there is. So it was a different thing. So traditionally what you had to do is, and how Woodin showed it's consistent, you start with a determinacy model, for instance, just with L of R. assuming large cardinals. This is a model of determinacy. You force with what's called Pmax forcing over this model of determinacy, and you arrive at this principal star. This principal star also tries to tell you that the universe, or at least an initial segment of the universe, specifically H omega 2 is rich in structure, so it's kind of maximal. You can formulate a strong maximality principle, which you may formally prove. So it's this kind of thing. Okay, the competing axiom here is the Star Axiom, which says that the axiom of determinacy holds true in L of R, plus there is a filter G contained in the forcing Pmax, which I do not introduce, such that G is generic over L of R, and you capture all the subsets of omega 1 in the true world by going to that forcing extension. If you force with Pmax over L of R, even though L of R is a determinacy model, it's not a model of choice. You create choice by forcing with Pmax, so L of R and G is a model of choice. And you say that the power set of omega 1 of V is contained in that forcing extension. There is a maximality principle, which I briefly want to mention. So maximality in this case is the following statement. You can, for instance, say if a pi2 statement, so this is a statement of the form for all x there is a y blah, about H omega 2, so these are all the sets which are hereditarily of size at most L of 1. If that's consistent, or rather omega consistent, this is a strengthening of the mere concept of consistency. Omega consistency is a strong form of consistency. You say that you have arbitrarily complicated models, and you have to define what that means for a model to be arbitrarily complicated. Then omega follows from star. This is one of the ways to spell it out. Okay, and now, these are two competing things. So what was known was that the Star Axiom, as well as Martin's maximum, they develop a very nice theory. Star is about a local rank initial segment of the universe. It talks about H omega 2. It doesn't say anything about the universe beyond that point, and it's not intended to say anything about the universe beyond this point. Martin's maximum is a global statement, but as far as H omega 2 goes, there was no consequence known which would be a consequence of one of the principles but not the other, but it was not known how the two compare. Okay, I want to finish, so I'm taking like 2 or 3 more minutes before I finish and we open the discussion by mentioning the following result. So MM, or forcing axioms, and star were two competing axioms which both decide 2 to the LF0 to be LF2. I had this picture up there. Maybe I should briefly go there again. So in this picture here, where we show a few of the implications of Martin's maximum, I could also put star there. So star has the same implications. And star actually also gives this principle A, which is written down here. So star would also give the same. So I could write a star here. And it is known that star implies A. These are all results of Euclid. Okay, and it was not known whether Martin's maximum implies this principle A. But if you go through the following result, you know that it's true. Okay, so there is a theorem which is from last year, and this was proven by David Asperó together with myself. And the result is simply, I was saying that we had these two sets of axioms, and it's also always nice and supporting in science if you can show that two principles which create a rich structure theory and explains a lot of things, if they are shown to be compatible, if you can kind of merge them, if you can unify them. And in this case, the unification is the simplest possible. The unification is simply that you show that one of them implies the other. So what more can you have as a unification of two theories, right? So there was this whole machinery of forcing axiom theory. There was this whole machinery of star theory. There were two industries, and you show that basically what you do is the same thing. The converse is easily seen to be false. So star by itself cannot imply one of these forcing axioms. This can be seen in many ways. Star is compatible with the fact that the universe is constructible from a subset of LF2, which is incompatible with any of the forcing axioms. So the converse direction is easily false, but the forward direction was shown to be true. So this used an elaborate forcing which we developed in this context. And let me finish with a corollary. That in the presence of large cardinals of a proper class of wooden cardinals, you have the following, that the following theories are equivalent. The following are equivalent. You have the star principle. And it turns out that the star principle is actually simply equivalent to a forcing axiom. And I'm not going to define it for lack of time. So what you say is it's a localization of Martin's maximum plus plus. So it is called bounded Martin's maximum plus plus. And also there are parameters here for sets of reals in L of R. So it turned out in the end that star, even though it has a completely different formulation, that it's simply yet another forcing axiom. So in some sense, you know, the forcing axiom theory was the powerful one and was the one which swallowed the star theory in the end. But in any event, so the forcing axioms, so the forcing axioms theory and the star theory got amalgamated or unified, which supports them both. And then you may argue, well, you know, you can take it as an argument, or you can make a case out of that. That might give a hint that that this theory actually produces the right picture, and in particular settles the continuum problem in the right way. So I'm very happy now to end my talk. I thank you very much for your attention.